And with the separated variables now, we integrated using the appropriate limits. And this will result to a negative ln of Ca over Cao being equal to K sub 1t. And correspondingly, from this particular formula, we can have Ca being equal to Cao e raised to negative K sub 1t. So I'd like to place a box on this because in this current scenario where the two rate constants for the two-step reactions are equal, the same formula as with the first that we have derived applies for the concentration of A at any particular time. So this is our formula. Okay, now we go to the intermediate R. So if we would like to write a net rate equation in terms of the intermediate R, in the first reaction, R is being formed. So I'd like to use the positive rate of change of the concentration of R. So this would be K sub 1 C sub A. Now in the second step, so if we go back here, in the second step, your R is being consumed. So it will be written as negative. So you'll have here minus K sub 2 C sub R. Now, if we will arrange our differential equation such that it would look like a standard linear differential equation, it would be something like this. And we can replace the Ca here with the Ca expression that we have already derived in the first page. So we can have K1 CaO e raised to negative K sub 1 t. Now notice that this K1 and this K2 are the same. So I like to write all K's as just the K. So I will have here, this is plus K C sub R equal to K, and then this K1 and K2 now being K, CaO e raised to negative KT. Now I have placed here let K sub 1, which is equal to K sub 2, be equal to K. Because anyway, the two are just the same. So if you recall the manner of determining the solution for a linear DE, there's a need for us to determine the integrating factor mu. So that would be, anybody who can recall how do we determine the integrating factor mu for a linear DE? What do we do? Anyone? Wala na gid sang may nakadumdum sang DE kung paano magpangita sang iya nga integrating factor. How do we get the integrating factor? So you've learned that we call this as the unknown function. This is our independent variable. This is your derivative. So in DE, if nobody recalls it, so in DE, your integrating factor is e raised to the integral of whatever is written here before the unknown function in the second term. If you recall, we call this the P of X. This one is Q of X here on the other side. So your P of X in this side is K, and that will be, of course, integrated with respect to time. So telling us that the integrating factor for this linear DE is e raised to KT. Now, knowing the integrating factor, you can now write the form of the solution of the linear DE. So I have defined already the unknown function and the independent variable. So the left side of the solution of the linear DE will constitute of the product of the unknown function and the integrating factor. So our integrating factor is e raised to KT. As what we have done here, we already determined it in here. And the right side constitutes of the integral of the product of your integrating factor, and in the DE, we call that the Q of T or the Q of X. Now, if we go back to our previous slide, our Q of X is everything here. Everything that appears in here is your Q of X, or in our case of the DE here, since our independent variable is not X, but rather T, we call this the Q of X. So all of this we will copy. So we will place it here. So you have times K CaO e raised to negative KT. And of course, it has to be integrated in terms of time. So this one is your Q of T. So I've copied everything here. That's your Q of T. Okay? This is how we write the solution of a linear DE. Now, left side, we copy still. And the right side, if you notice, by rules of exponents, this will be e raised to 0 or 1, leaving you to integrate K and CaO. So this would be K CaO T. Okay? Now, of course, you will have this arbitrary constant of integration. I'd like to place a prime on it, knowing that it's a constant. So you have CR times, or C sub R e raised to KT is equal to K CaOT plus C prime, where C prime is the arbitrary constant of integration. Okay, now before we do anything else, we have to find what this arbitrary constant is, or we have to really determine what it is. We cannot let it as is as C prime. So we need to, of course, use the appropriate condition in the problem. So in the problem, it's stated that at the initial at time equal to 0, the initial concentration of R, which is CRO, is equal to 0. So we can apply it in this equation. That way we can find the actual value of C prime, or the actual representation of C prime. So if this is 0 and this one is e raised to 0, so the left side is really 0. And you will have K CaO, that would also be 0 plus C prime. Therefore, we can say that our arbitrary constant of integration C prime is just equal to 0. And our final expression for the concentration of R at any particular time will be, I'd like to copy this, K CaO, and this one I will transfer in this side. So it will be now e raised to negative KT. And you have here T. Okay, so C sub R is equal to K CaO. I've copied this too. I have inserted this one, which was used as a divisor in the entire formula in transferring the exponential expression here on the right side. That would be this one. And then you have the time. Now, this equation allows you to solve for the concentration of R at any particular time for a two-step irreversible reaction in series when all rate constants are equal, meaning K sub 1 and K sub 2 are equal, and with the scenario that we don't have any initial amount for the intermediate and the final product. But we have, of course, an initial starting value for the concentration of A. Otherwise, there's no point in solving anything. Okay, so this is it. Now, but the thing is, the problem did not ask us to find the formula for A, R, and S at any particular time in this scenario, but rather the maximum concentration of R and the time when it is maximum. Though it's not specified in the problem class, so the problem did not specify that we are to determine the three formulas, we will just determine it now. That may later on, when you encounter such a situation, you can directly, I will say it, you can directly use the formula that we have already derived. There's no need for you to derive it all over again because we already derived it. So then the next step that we will find here is to find, so I will go to the next, have another sheet here to find the C sub S. So as a review of what we did last Monday, how do we find the concentration of C sub S? For a series reaction consisting of two irreversible steps. How do we find C sub S? Are you there, class? Am I not alone here? So there's 16 of you. How do we find C sub S? So we have discussed that CaO is equal to Ca plus Cr plus Cs for a two-step irreversible reaction in series. And this is still a constant, that's CaO. This Ca is CaO e raised to negative Kt. And your C sub R is the C sub R that we have here. You have K CaO e raised to Kt times T. CaO, okay, e raised to negative Kt times T. So that's it. Okay, we'll make negative. And you have the C sub S. So your C sub S is equal to CaO minus CaO e raised to negative Kt minus K. I like to place the T here. Kt CaO e raised to minus Kt. Since all this have CaO, you can write Cs is equal to CaO times 1 minus e raised to negative Kt minus, why is this minus? Okay, I've transferred it on the other side. Kt e raised to negative Kt. So you have now a formula to use in determining the concentration of the final product for a two-step irreversible reaction in series whenever the two rate constants K sub 1 and K sub 2 are equal. So I just presented it here, that way you will have a ready-made formula later on to use should the need arise. But we haven't really determined what the problem required. So let's go back to what the problem required. So the problem required, in the same way as the one that was presented in the discussion part in the text, requires you to determine the maximum concentration of R and the time when this particular maximum concentration occurred. So that I would like to ask anybody, how do we find the maximum concentration of R in this case? Anyone? How do we find the maximum concentration of R at this time, given this scenario? You have learned already the tool before. How do you find maximum, minimum values? How do you find the maximum concentration of R? Okay, so let me see what's placed here. Optimization. Explain optimization, Marcel. I'm asking a simple question. How do you find the maximum concentration of R? So you say, okay, we've learned it probably before in the topic of optimization. Okay, if you've learned it in the topic of optimization, give me a simple instruction on how you will find the maximum concentration of R. How do you find the maximum concentration of R? Very good, Joshua. Differentiate your equation. You differentiate this. You have already done, you're done already with the application of the derivatives in EMMA 101. So you have to differentiate that particular equation. So I will write it here. That way we can differentiate it. So your formula is C sub R is equal to K CaO e raised to KT. KTCAO. So I forgot the T. You paste the T here. Hi. So that's our formula. So you will differentiate. So you get the derivative of R with respect to time. So since you have two expressions which has the T, this 2 is a constant. So you use product rule for this 2. The first term times the derivative of the second minus the second times the derivative of the first. Now, the derivative of EU is EU du. So you have K. Do you get it? Then we set this to 0. So it's now 0 equal to, so we get rid also of KCAO. So you have E raised to KT minus KT E raised to KT. If you notice, you have this. You have 0 is equal to E raised to KT times 1 minus KT. So you have 0 is equal to 1 minus KT. So your T is equal to 1 over K. You transfer it here, 1 remains here, so that would be 1 over K. Yeah, there's something written on the chat box. Miss Negative Guru ang KT. Wait. KT. Thank you, Josh. Negative. Anyway, we get rid of this expression. So we're left with this one. But nonetheless, it has to be negative. So your time when C sub R is maximum is this. This is the first answer. The time when C sub R is maximum. Now, what is that maximum concentration means that you will substitute this formula in here for the time. So we will have another one here. So your C sub R is equal to KT CaO E raised to minus KT. I forgot the negative sign here. Okay. Okay, class, I need to pause. There's a call that I need to take. Okay, so we will substitute 1 over KT in here for the time. So C sub R maximum is equal to K. This T is 1 over K. CaO E raised to negative K, and this is 1 over K. So your T will be 1 over K. So we cancel this and we cancel this. Your maximum concentration for R is CaO E raised to negative 1, or that would be CaO over E. Wait, huh? You substitute 1 over K here, right? And you substitute 1 over K here. So negative 1. So this is the maximum concentration of R. In the scenario we're in, your rate constants for the first and the second step of your two-step irreversible reaction is equal. You can get the actual value of 1 over E and place it here. So you can have CR maximum equal to 0.368 CaO. Okay? Please check if that's correct. So you have 0.368 CaO for the maximum concentration of R. But that's only for the scenario we're in. You don't have any starting amount for R and S. If there's a starting amount for R and S, this one will not work because you have to appropriately substitute the initial value of R in here. Well, will you substitute here in finding the C prime? This one. So if your C sub R is not equal to 0, then there's a corresponding value here that you will place. And C prime will not anymore be 0. So you will have another term here And you will have to substitute the correspondingly the time when C sub R is maximum and get a different maximum concentration of R in the process. Okay, but for this one, this is the answer. Any question? Any question? None so far. So that's how we apply the procedure, the concept that Levenspiel illustrated in the derivation in his book. So we will continue to, we're done with irreversible reactions in series. So now we will go to reversible reactions in series. Okay. So I have mentioned this, that all reactions actually have a certain degree of reversibility. So many reactions are reversible due to the fact that no reaction ever goes to 100% completion. It's so ideal that there's no such thing as 100% conversion of the starting material to the finished product. So irreversibility of the reaction increases as the equilibrium constant K sub C increases. Later, you will note that this K sub C, the equilibrium constant, which is also represented as K with a subscript EQ, is dependent on the rate constants. So we have a formula in which it's based on the rate constants, or it's based on the concentration of the species raised to its coefficient in the provided chemical reaction, but these particular concentrations have to be measured at equilibrium. So we have two sets of formula for the equilibrium constant. Why is it now going straight to this one? Okay. Okay, so duha lang mandigali. Now we go to the first order reversible reaction. So first order, we have the single species on the left side of our reversible reaction. Now in the scenario here, you're forming R from A, and the initial concentration of R divided by the initial concentration of A is represented as M. If we will write a net rate equation based on the two reactions considered as elementary, this is how we write it. So rate of formation of R, it's positive. Rate of disappearance of A, it's negative. In terms of A, it would be this, discussed already. And in terms of A is being consumed in the first reaction. So since it's negative here, so it's already positive in here. K sub 1, C sub A. And A is being produced in the reverse reaction. So this would be negative. So now K sub 2, C sub R. Because in your second reaction, A is acting as a product. So you have to look at this reversible reaction as two reactions. This one is for the forward reaction. So you have K1. And this one is for the reverse reaction, K sub 2. Okay. So when you write the net rate equation, it would be based on these two reactions coming from the original reversible reaction. Okay. If we will solve the DE based on A, there is a need for you to change the C sub R in terms of C sub A. Now, the C sub A here was changed into the form wherein CA is equal to CaO times the quantity 1 minus XA. So it looks something like this when expanded. And your C sub R here was expressed in terms of the conversion of A. Your C sub R was expressed in terms of the conversion of A. How is that? So we know that your C sub R is a product. If this reaction is taken as a whole, your C sub R is a product. So we write it as CRO 1 plus XR. And we have it as CRO plus CRO XR. But in terms of stoichiometry, your CRO-XR is just equal to CaO-XA. So you have to change the CRO-XR here to CaO-XA. I like to write it here so we will have continuity. So you will have now C sub R is equal to C sub RO plus CaO-XA. right? And then since M is being introduced here, then that M is CaO, or rather CRO over CaO, then this particular equation was actually multiplied to, this is still CaOXA here, K2M. Okay, this one, sorry, is just this. Why? Because your M, I'll write it here, your M, which is CRO over CaO, times the CaO here, this one, is just the CRO, the original CRO, and you have here CaOXA. Okay, so this formula is just the same as this one. So you have now a right side for this particular DE that is dependent on the conversion of A. It follows then that the DE that you will process will be CaO dXA dt equated to this whole expression in here. Okay? CaOXA is the CaOXA. This MCaO is your CRO based on what I have presented here. So these two expressions are actually equal or the same. So that's in terms of the formula that we can use in processing or determining the unknowns for irreversible reactions, or rather reversible reactions, first order in nature. So I'd like to go down to the next slide. Sorry, class. And this is the expression that I said regarding the equilibrium constant. So for a first order reversible reaction, the concentration of R at equilibrium raised to 1, because this is 1, divided by the concentration of A at equilibrium also raised to 1. If this number, if this, shall I say, if the coefficient here is not 1 in this case, then you have to correspondingly, in this particular formula, change the exponent here, which is 1. So to the appropriate coefficient that appears in your first order reversible reaction. Now, this CRE was expressed again in terms of equilibrium conversion. Now, as an exercise, I will leave this to you to derive so that you will learn out of the derivation. The CAE we know is CaO1 minus XAE. The concentration of A at equilibrium is the initial concentration of A times the quantity 1 minus the equilibrium conversion of A. So this one is this. The CAE here was left with this one. So meaning there was a division that happened while the CaO is gone. But nonetheless, it's important based on what you've learned in Chem 1 that the equilibrium concentration is this and this one. The ratio of the rate constants for the forward and reverse reaction. This one is the ratio of the products raised to their corresponding coefficients in your provided chemical reaction divided by the product of the reactants also. Their concentration of equilibrium that is raised to their coefficient in the chemical reaction. So these are the two basic formulas you know. Now this one is yet to be derived. So, but this is an equivalent for these two, a way of expressing the equilibrium constant in terms of equilibrium conversion and the ratio of the product and the reactant initially. So CRO over CaO is your M. Now, if you will substitute this particular expression in the equation that we have here, this one, this equated to this XA, because our variables here are XA, you have already a ready-made formula to use for the conversion at any particular time for a first order reversible reaction, and the conversion at equilibrium. This one class, this XAE is a constant, the equilibrium conversion, whereas this XA is not. Now, this is also equal to this expression, and now you see again the M appearing. So this formula allows you to determine after some time what would be the conversion of A, or after some time what would be the concentration of A, provided that you are given the constants, fractional conversion at equilibrium, and the constant concentration of R and A, because we have the M here. So this is already a ready-made formula. We will not derive it anymore for the sake of saving time. So note, all first order irreversible reactions are actually a special case of reversible reactions in which the equilibrium concentration of A is 0 and its equilibrium conversion is 1, and it's said to be that your equilibrium constant is infinity, meaning it's very, very big. Okay? So that's for the first order reversible reactions. If you will ask me what formula, we have to take note of, miss, and understand how it came about, this one for your first order reversible reaction. Now, we also have second order reversible. So this one, you can have this scenario, you can have this scenario, you can have this, or you can have this. Okay? Now, in the formula that you are seeing here, because it's already pre-derived, given to us in the textbook, this will only work, this formula will only work if we're starting with the same initial concentration of A and B. So meaning we're talking of scenario, this one and this, wherein we have two reacting species, and that we don't have initial amounts of the products formed. R and S are 0 and A and B are equal initially. So the corresponding rate expression, so meaning you have to write a rate expression just like this one class. We wrote a net rate expression for the rate of conversion of A in this form, and then change it to this form. Now you have to do the same thing in here for these 4 possible scenarios for the second order reversible reaction. But in this particular formula here, as I've said, the only condition that will apply is this. So meaning I change one condition, this is not anymore true. So meaning there's really a need for you to know how to do, find the formula, the working formula for a particular reversible reaction, provided you are given the reaction itself. So kinahanglan kabalo ka mag-set up sa imo net rate equation. That way, if there's a condition that will change, you will know how to derive the formula later on that you will use in finding the required information in the problem. This one will work for the condition that is given here. Now, the sample problem I chose to discuss, because there's none in your textbook to use, is this one. And it's not similar to any of these two. That way, you will more or less know have an idea on how you will set up your own working equations when the scenario is not similar as the one that is provided in the pre-derived formulas in the book. Okay, so this is our sample problem. Okay, let me read this first. Now, you're given the reversible gas phase decomposition of nitrogen tetroxide to nitrogen dioxide. It is to be carried out at constant temperature. The feed consists of pure dinitrogen tetroxide at 340 Kelvin and 202.6 kilopascal. So the equilibrium constant K sub C at 340 Kelvin is 0.1 mole per decimeter cube. Calculate the equilibrium conversion of dinitrogen tetroxide in a constant volume batch reactor. Look at this particular reaction that's provided. It's neither of the two, because in the forward reaction, if it's considered elementary, it's first order. In the reverse reaction, it's second order. Unlike the ones that were given in the book, wherein both sides agree in terms of the order. First order in the left, forward, first order to the reverse. In the second one, second order forward, second order reverse. This one is not. So then there's a need for you to write down the appropriate net rate expression for this particular problem. Okay, and we will have to do that. Let me go to our whiteboard. So our given is nitrogen tetroxide. So here I go again. I was not able to take a picture. Let me go back, please. Okay, so we have the problem already. So I can read through each of the statement and we write down the information that we need in the given part. So do whiteboard again. So nitrogen dioxide here on the right. Reactant is dinitrogen tetroxide. Right is nitrogen dioxide. So we started with pure dinitrogen tetroxide. So at T equal to 0, we have pure dinitrogen tetroxide. And this is at a temperature of 340 Kelvin, a pressure of 202.6 kilopascal, and an equilibrium constant, or a K sub C, which is 0.1 mole per decimeter cube. This is at the given temperature. Now, before I forget, in kinetics, by the way, class, we specify the equilibrium constant, whether it's in terms of concentration, we're dealing with concentration, or in terms of partial pressure. In this problem, we're talking about gases. So it could also be that your equilibrium constant could be represented in terms of K sub P, meaning partial pressures of the components will be considered in lieu of concentrations because this one is a gaseous reaction. But since the problem specified that it's a K sub C, then we're not really actually given, or we're not to work out on partial pressures in terms of the representation of the concentration, although we can if we want to. So this K sub C can be changed to K sub P for the case of gaseous reaction. But in the case of homogeneous liquid reactions, it's really K sub C. Okay, so you are required in this case to find what was required? You are required to find the equilibrium conversion in a constant volume batch reactor. So now it's really specified that it's a constant volume batch reactor. You will learn when we discuss already variable volume batch reactor that it's really different when the problem does not specify that it is constant volume, especially if the reaction is gaseous in nature. But since the problem here specified that this is at constant volume batch reactor, it has to be written here. You are asked to find the equilibrium conversion. Now, what will happen if you're given a gaseous reaction and the problem is silent whether the reaction is performed in a constant volume batch reactor? You are to solve for a certain parameter. That certain parameter we will discuss when we're there already. You are not to assume that it is performed in a constant volume batch reactor unless otherwise it's stated. What about if the reaction is liquid? There's no need to worry whether it's a constant volume or batch volume, constant volume or variable volume batch reactor, because most of liquid reactions are constant volume. It's okay to assume that it's a constant volume reaction unless the problem says that it's not. But for gaseous reaction, there's a need for you to measure or determine a certain parameter before it's okay to assume that it is being performed in a constant volume batch reactor. Okay? Now, our problem is in the equilibrium conversion of A. So we have to write an expression that would lead us to the equilibrium conversion based on what we can work on, based on what the problem provides as information. Now, I'd like to ask a suggestion from you, or if anyone here has an idea, what would be the starting point, the appropriate starting point in this problem, since you have equilibrium conversion of A that is being asked? Or how will you start solving, since it's equilibrium conversion that is being asked and you are provided with this information here? Anybody? Or what is it in the problem that is connected to conversion in the first place? Or what is it in the given that is connected to, has some relationship to conversion? That's how you solve a problem. Ano diri sa ginhatag sa imo nga info nga more or less may connection sa ginapangayo iya nga conversion. What do you think? Is it this one? Is it this one? Okay, we talked a while ago about the expression for case of C, right? Or the equilibrium conversion. So I will write here equilibrium conversion, and it's equal to 0.1 mole per decimeter cube. Now, you have two formulas here, right? That you can use. One is ratio of rate constants, which is not provided in the problem. And the other one is equilibrium concentrations. So we have in here, we have nitrogen dioxide and dinitrogen tetroxide. So we don't have to copy the formula for these two species. We will represent this as A and this one as B. So this is A and this is 2B. Okay, we'll just return A to N2O5 and B to NO2 later when we're done. So when we speak of equilibrium constant for this particular reversible reaction, you've learned in Chem 1 that it should be equated to this equilibrium constant, the equilibrium concentration of the product B. I represented the product as B, divided by equilibrium concentration of reactant A. This is squared. Why did you square it, miss? Because your reaction here has a coefficient of 2 for B and a coefficient of 1 for A. You get it? Are you there or am I alone? Again. So this would be it. Then I will change this to, then we cannot use this because we're not provided with rate constants. And we can have CA, sorry, I'm so used to A. So CBO 1 plus XBE. Squared, squared, squared and squared because this is squared. Y plus because B is a product. You just change the XB here to XBE to connote that it is representing equilibrium conversion for B. For A, CaO, this time it's 1 minus XAE. Why? Because A is a reactant, so it should really be 1 minus XA. The Kc that you have, which is 0.1, I'll place here, will now be equated to the expanded form of this expression. So you have CBO squared. I will have this expanded, so 1 plus 2XBE, excuse me class, plus XBE squared. Denominator is CaO 1 minus XAE. Remember, the required information is what? The required information is this. We're not after XBE. So there's a need for you to find the equivalent for that. So I will continue. So the expanded 1 plus XBE quantity squared will be now multiplied to CBO. So the CBO squared. So this is squared. Plus 2 CBO XBE. This is squared. This one is 2, sorry. CaO, CBO, XBE, both are squared. So I'll place here squared over CaO 1 minus XAE. CBO, so what did the problem say about CBO? Okay, we did not read that part. So it says that, what is my problem saying about CBO? Let me check. So says here, the feed consists of pure N2O4. So meaning initially, you don't have B. The feed consists of pure N2O4 as written here. So you don't have B initially. So if that is the case, since we have pure feed, this is 0 and this is 0. This one, you cannot set to 0, otherwise you won't be able to solve anything. But you can replace this with a different expression. So I will have here 0.1 being equal to, what is left in the numerator is CBO XBE squared. Denominator is CaO times 1 minus XAE. Equation 1. In our stoichiometry, CBO XBE, 2, 1 here. So the amount formed from A divided by 2 is the amount coming from A divided by 1. So then the CBO XBE is twice of CaO XAE. So this is your equation 2. This one you will substitute in here. So you have a 0.1 equal to CBOXBE is twice of CAOXAE. So this is twice of CAOXAE. This has to be squared because this one is squared and this one is not. So CAO 1 minus XAE should be copied in the denominator. So in here, you get to cancel the CAO, but you still have 1 left in here. So you have 2 CAO XAE squared all over 1 minus XAE. This is substituting. That would be substituting 2 to 1. So this would be our third equation. This is your expression. So this is your third equation. So tell me, I have one unknown to determine before I can find the XAE. What unknown is that? What unknown is to be determined before we can find the equilibrium conversion of A? That would be the squared Japon ang 2. Thank you, Aliana. Yes, it has to be squared, Iha. So this is 2 squared. So that should be 4. What should we find then to be able to find XAE? We cannot solve XAE because we still have one unknown. What's this unknown? What is this unknown? Anyone? What is that unknown? That would be the CAO, miss. Correct, Joshua? CAO. Maano na lang ko kung wala si Joshua, si Aliana. Kaya ako na lang gidiri isa. So you need to find CAO. How do we find CAO? How do I find CAO? PAO over RT. We started with pure dinitrogen tetroxide. So we will use the pressure that is given to be the pressure of the entire dinitrogen tetroxide because we don't have any of nitrogen dioxide initially. So we will use this. So we'll go back here and use 2.026 times 10 raised to 5 Pascal. Then the R that we'll use is 8.314 Joule per mole Kelvin. Then we use the temperature 340 Kelvin. So we cancel the Kelvin and the remaining expression here, the Pascal is Newton per meter squared. This one is Newton meter. So the remaining unit will be for mole per cubic meter. In that case, you have 71.67. Okay? Then you go back to your original, to your equation 3 and substitute this one. The problem is this one class, the unit of this is mole per decimeter cube. So you need to convert this one. Your 71.67 mole per cubic meter should be converted to mole per decimeter cube. So that would be like 1 meter to 0.1 decimeter. Then we raised it to 3. So this would be now 716.7 mole per decimeter cube. So this is the CaO that you will substitute here to find the equilibrium conversion. So we will do that in this next slide. What's happening? What's happening with you? Okay, so you have 0.1 is equal to, so I have a 4 now because it's 2 raised to 2 in here. Here's, yes. Miss 1 meter is 10 decimeter. Ay, right, gamay gali and decimeter na man si Miss Man. So it should be 10. Anyway, so pila na ni sa Josh. So 10 decimeter, so divided by 1,000. So this would be, okay, thank you, Josh. So you have here 0.07167 mole. Ay, again. Oh, right, 1,000. Okay, raised to 3. Mole per decimeter cube. Dako pa ang decimeter sa meter ba? Anyway, so you have that 10. I got it interchanged. Okay. Now, where was I? So 0.07167. So 0.07167. That's for the CaO here. And the XAE. That is to be squared. Squared 1 minus XAE. So you will have 2 equilibrium values. Can you please check what are these 2 equilibrium values? Of course, you need to validate which one is acceptable. Can you please check? Excuse me. What's our XAE? 0.44 cog negative 0.79. So you have 0.44 and negative 0.79. Thank you for that. So you need to validate this one. We don't have a negative conversion, right? So this is not acceptable. So this is your equilibrium conversion of A in the provided condition in the problem. Okay? Sige, before we go to the next part in the slide, it's a new topic. Would you like to ask any question? You can type in the chat box if you don't have headphones, microphones. So none? Sige. So we will continue with the next topic. Okay, this is where we ended on reversible reactions. And now we go to reactions of shifting order. Or simply, how does the order of the reaction shift or is changed with the change in the concentration of the reacting species? Or how is the order of the reaction, how is the order of the reaction being affected when the concentration of the reacting species is, shall I say, changed? Like, let's say, for example, can you see my slide? You can see the slide.
Yes, miss.
Okay. So you are given this particular rate equation. Now, the question in here is just simply the problem, or the problem will be asking you what will happen to the reaction order if concentration of A is high. If we have a very high concentration of A, this is very high, and this is very high, this one will be very negligible compared to this one, which is very high. So as such, it's as if one does not compare to the second term. If that is the case, one is out of the picture, and it seems like what you have is just this, a K1CA over a K2CA. When C sub A is very high or high, and that is the case, the reaction is already zero order. Reaction is zero order with rate constants K sub 1 and K sub 2 because the two concentration terms cancels each other out. That is in the case of a high concentration of A. What about if A is low? What about if the concentration of A is very low compared to the, let's say, the number 1 that you have in the denominator? What's the matter with you? Okay, if it's very low, it's like this one does not compare at all to this. It's like this one is 0.000 something and this is 1. So it's like it's not there. So what you have is the numerator K1 C sub A over 1. That is why the reaction is of first order with rate constant K1. Okay, first order with rate constant K1 because it's the only thing that appears in your remaining expression. When you are asked a question similar to this, you will be provided with the rate equation. And you would be asked, like, what will happen to the order of the reaction if this is very high compared to this, or if it's very low compared to this. So the principle that you're going to apply is similar to what I've discussed in here. It's very simple, actually. It's just like one being small compared to the other, or one very, very big compared to the other. So you take one out of the picture, one remains. And how is the expression being simplified out of that particular scenario? Just like what we did here, how it was simplified now tells you what would be the corresponding order of the reaction. Simplify first before you conclude what is the resulting order of your, of your reaction. Okay? Question? Okay, so if there's none, we are on the last part of the constant volume batch reactor interpretation of data, and that's the differential analysis. So in integral analysis, from the term of the analysis itself, you know you're going to use integral calculus in dealing with the rate expressions themselves. Okay, you're going to use integral calculus in dealing with the rate expressions themselves that best represents your given reaction based on the provided data. So you use integral calculus. When do you use differential analysis? Now, you use differential analysis when the bulk of data that is provided to you, let's say class, is more than, let's say, 7 pairs or 8 pairs. There could be data that will be like 20 pairs of data. You cannot use integral analysis with such big bulk of data because that would take time. So it is suggested that you use differential analysis. Anyway, it will be discussed in the succeeding slide. But nonetheless, differential analysis class, if you're going to ask me, is crude compared to integral analysis. Why? It's very crude because of the following steps. So I will not tell you the reason. You tell me the reason later after I have already discussed the steps. If you're provided with concentration and time data, you are to plot the concentration and time data. Concentration on the Y, time data on the x-axis. That's the procedure in differential analysis. So you really have to plot. Now, next step is you draw by eye. What do we mean by drawing by eye? Drawing by eye means that you are to draw the best fit curve out of the set of points that you have placed on the C sub A T axis that you have. You are not to connect all points, but rather you are to draw the best curve that will be nearest majority of your points, or that would be passing through a majority of the points that you have plotted. So by eye, draw a smooth curve to represent the data. The curve does not need to pass through all the experimental points, just like when we find the best fit line. The best fit line need not pass through all the points that you have plotted. Now, drawing by eye also means that it's dependent on how well you draw your best fit curve. The best fit curve of Joshua may be different to the best fit curve of Aliana or Joburn, Katrina. So your answers are all varied in this case because it's all dependent on how well you have drawn your curve. Okay? Determine the slope dCA dt, which represents the rate of production of A or the rate of disappearance of A of this curve at selected concentration values. Now, this step here is quite vague. If I will just simply discuss it or read the, shall I say, the statement. So this is what you're going to do. I'll have here one new sheet. Example. You have here your C sub A, and this is your T. And you have points. Okay, you plotted your points. That's first step. Then what you do, you draw your best fit curve. My best fit curve may be different than yours. So let's say this is my best fit curve. Let's say that's my best fit curve, or it could be somewhere here in the below. But that's just the way I seem to look at it as my best fit curve. The third step is asking you to do this. I need the different color that you can see on the red. What is happening to you? Okay. You are to, on selected concentration points, meaning I'll probably get one concentration point here, and probably one concentration point here, one in here. Okay. I think I need to settle only with 3 because it's difficult for me to draw a tangential line. For each of the concentration points I have selected, I will draw. So that's what the step, go back to the slide. That's what step 3 is saying. Determine the slope, dCA dt, of the curve at the selected concentration value. When you find the slope, what do you do? When you find the slope of the curve at the selected concentration value, let's say I want to find the slope here, here, and in here. What do? You what? You draw a line tangent to the curve at that selected hindi siya every time maghambal ko, nag-draw na siya. The selected concentration point. So this is like this class. Very crude, but nonetheless, I'll draw a tangential line here. I'll draw a tangential line here. I'll draw a tangential line here. Of course, it's not tangential the way I draw it. I will find the slope. That slope is dCA dt. That's negative r sub a. This one will have its own, this is later na, also dCA dt. Let's say negative r sub a 2 ni, r sub a 3 ni, and this one will also have another slope, dCA dt, and it would be negative r sub a 1. What I have now is something like this. For my CA values, I have 3, right? The blue points here. Hey, the blue points here. I have 3 concentration values. I will find the slope of this line. You know how to find the slope of the line. You draw the line, you get 2 points on the line and solve for the slope. You read the corresponding y and x. Corresponding y and x. Get the difference, the ratio of the difference, that would be the slope of this line. So you will have here r sub a. You also have 3. Right? That's differential method. You plot, you draw the best fit curve, select. So the selection again will be dependent on you. Your selection, one student may select 3 points, the other may have 5, depends on the student. So the slope at those particular points would also be different. Different CA, different slopes. Slope, this one, the rate of change of the concentration with respect to time, the slope of the tangential line on the selected concentration points on the curve. Okay? Then next, we go back to our slide. Next would be plot ln-CA versus ln-RA. The linearized nth order form of the rate law together with the equation of the best fit line will give the order of the reaction and the specific reaction rate constant. So meaning, though you already have the CA, you already have the RA, as I have placed in the whiteboard a while ago, you are to get the ln of those two. The linearized nth order form of the rate law, meaning you will make one as x, the other one is y. You linearize it, the corresponding slope and y-intercept of that particular best fit line will give you the order of the reaction and the specific reaction rate constant, or simply the reaction rate. How is that me? So let me go back to the one that we have started. So you have this. After this one class, we'll make a black one. We'll use the black one. The data that you will really get the best fit is ln-CA, ln of negative RA. So since you have 3 there, you will have also 3. ln of CA versus ln of RA. Now, let me make this smaller. Why do you have to get this? Remember that when you write the rate law for a reaction in which you do not know the order and the rate constants, it's something like that. If you take the ln of both sides, you will have something like this. The ln of RA is equal to the ln of K plus the ln of C sub A raised to N, which is right here, the ln of the rate equal to N ln of CA plus ln of K. Now what's this? This one is your Y. This one is your X. This one is the M. And this one is the Y-intercept. So the coordinates here, the pair of coordinates that you have here for the selected concentration values, and the slope of the lines on those concentrated values will be processed by taking the value of their LNs. So your LNCA is X and ln of RA is Y. Then you again find the best fit line equation. Now the slope of that line gives you the N, and the y-intercept of that line will help you solve for the K, which is the specific reaction rate constant. That is the differential method of analysis. Now, I'll go back to the question I gave a while ago. Why do you think did I say that it's a crude way of finding the rate expression? Why is the differential method of analysis a crude way of finding the rate expression or the rate law that will represent a set of data? Why do you think it's crude? Just give me one reason. Why do you think it's crude? Anybody in the house? I have, oh. It's crude means since from the start using graphical method of assigning points and drawing the line deviates from the true values. You have your point. Having to draw the best fit curve from the, thank you, Jobern, having to draw the best fit curve out of the raw data that is provided in the problem is already dependent on the skill of the one who is drawing the best fit curve. Look at my best fit curve. It should have been somewhere here, right? Somebody might have drawn it somewhere here. So it's already crude. My answer is different than the one who had a curve that is more or less, let's say, representative of the points that were plotted. In the first place, when you plot points, not everybody have the same plotting of points. Not everybody has 20/20 vision. So in that case, the plotting of the points in itself will be different from for all of us. So the plotting in there is already one reason why it would be crude. Let's read another reason here. Kay lain-lain matamis ang kada solve. Tsakto na. It depends miss on the selected points and the best fit curve. Correct, Katrina and Sarah. Now, nakadraw ka na curve. Naka-plot ka na points. Dito pa lang daan ba? Hindi kaya may vision mo, lain mo plot. Pag draw mo pagig curve, kasi lain ang curve ni Katrina, lain yan ni Sarah, lain kamutanan curve. That's one, ang pag-select pagid ng concentration points. Sa different na nga curves, of course, ang resulting concentration points would be also different. Kag dason ti makwa kapal sa iyan sina ang slope. So ang process in itself will not be consistent, shall I say, will not be uniformly done by all persons who are using it. Now, the big question is, it's crude, but it has to be used. Why it has to be used? Because there are really empirical data that are in bulk. So kung imo sa gamitan integral analysis, kag magsagi ka trial and error finding N that will solve for the same values of K, or sagi ka guess test, ayawan kay kadamo-damo sa data nga imo i-process. So amo na nga may alternative kita nga what we call differential method of analysis. Though sa aton di sa Pinas, aton subong current condition, we say it's crude because we're doing it mano-mano. But if you have a graphical calculator that can draw the best fit curve for you, we can say that that crudeness would be more or less addressed. Kaya ang calculator niya ang nag-draw sa imo curve mo, ikaw may set kung anong degree sa imo curve. So meaning then everybody would still have different representation of the curves. But nonetheless, it will not be as crude as what we're doing here wherein I gave a student or I assign a student to bring a graphing paper, plot and draw your best fit curve and choose your concentration points and so on and so forth. But nonetheless, it's important because if you're dealing with the bulk of kinetic data, integral method of analysis is not really practical. In the first place, if you're going to have the guessing and the testing, it's not anymore practical. Though we have the empirical rate equation, you still have trial and error. If you have a program, though, that will continue to loop until you have the same K values for the assigned end, then good for you if you have made that program already. And actually, it could be done. But still, integral analysis in terms of time is lesser only. It will only use less time if we have less amount of data to process. Okay? So far for now, this is the first part of interpretation of batch reactor data. And we're talking about constant volume batch reactor data. And we're done with the longest part of the slide. The variable volume data, I'd like to transfer to our slide now. The variable volume data in here will be repeating everything that we have discussed, but this time the volume is varying. The volume is varying when, number one, when reactions are gaseous in nature. So if it's not liquid reactions, you are not allowed to assume that your volume is constant unless the problem says so. So automatic na giniya klase hindi na magpamangkot nga misma solve pa ko amo ni mis pangitaw automatic. If it's a gaseous reaction, you have to solve for what we call as the fractional change in the volume, which we will be discussing on Monday. Actually, I will just give you the idea of varying volume batch reactor. It starts with, or I will have to stop share. I will share the raw slide without projection so that I will not have to click so many things. We are on slide 51 of 60 slides. So meaning I have 9 slides left for varying volume batch reactor because we'll just be repeating everything class with a different set of formula because our volume is varying. Where is that? Here. The volume at any particular time is equal to the initial volume times the quantity 1 plus epsilon A XA. This fractional change in the volume between 0 conversion to 100% conversion is the parameter that I have been referring to you a while ago that you need to determine. You need to determine before you continue solving problems in gaseous phase reactions. I always suggest to my student that whenever you're given gas phase reaction, always start with determining epsilon A. That way you will not forget that you're dealing with a gaseous reaction. Once you have already determined the final volume with the initial volume, the formulas will change for the zero order reaction, for the first order reaction, for the second order reaction. Then that's for the integral analysis. For the differential analysis, you will only add something to you will just change something to the information that we are plotting. But I don't want to burden you with that now. I can discuss this on Monday for 2 hours. So this is the remaining topic consisting of actually around 8 slides only. 1, 2, 3, 4, 5, 6, 7. 7 slides to be discussed, but of course there has to be problems that will, sufficient amount of problems that will illustrate the use of these formulas. So the same set of scenario but varying volume. You may ask, Misty, wala na multiple reactions nga gas phase, wala na. Ang aton multiple reactions starting with parallel, homogeneous, autocatalytic, series, reversible, we will apply it to homogeneous reactions, meaning liquid reaction siya, pero gaseous reaction man siya pwede as long as it's constant volume, just like the one that I have discussed a while ago. But we will not have those types of reactions when the volume is now varying, okay? here. So 7 slides on Monday, and of course it's expected that you will have something to do. You will have your last quiz on Wednesday for kinetics. Okay, I will give you the last problem set. Probably I can give it on Thursday, and you will submit it 2 weeks after. That way, you will not really be forced to submit it if you have other things to study, but it's really meant for you to practice solving, because it's different when I am here to guide you, and it's different really when you are the one really having to start solving a problem from scratch, having to know everything. How will I solve this particular problem on my own or with my classmates to collaborate with? So I will really give you a problem set, a last problem set. That way you will know what to expect, because I don't want you to just simply, oh my, what are these things that Miss Ali is giving us during the exam? I don't have any idea. So you will have an idea on what to expect in the exam. Then I will be giving you the last problem set. More or less, that would mean that if you prepare for the exam, you practice solving the problems that I'm giving you. If you're able to solve those, then you are ready for the exam. Because normally the problems I'm giving are, shall I say, more or less 50 to 60% comprehensive, meaning it's not only using one particular concept, but rather it's already a mixture of concepts that we have discussed from the very beginning. Okay? Any questions? So, we're done with this. Monday naman ang nabili niya, 7 slides with sample problems. I will give you within the week the last problem set for you to start solving. And by the way, I will place an announcement in the GC because some are not with us this afternoon. I don't know. There's only 14 of you.